Hey guys, so in this little video, we're going to look a little bit at how enzymes speed up the rate of reactions, right? How they function. So enzymes are very important to living things because living things need their reactions to occur at fast rates, faster than would happen naturally, and at very specific rates. Right? We're trying to maintain homeostasis. We want to keep systems going. We want reactions to occur at our pace. We don't want to wait for the reactions to occur at their own pace. And so enzymes are critical to life functioning well. And enzymes speed up the rate of reaction by reducing the activation energy of the reaction that it's involved in. As a reminder, it is a catalyst, right? So it is not being used up in the reaction itself. So a little bit of enzyme goes a long way because they do the reaction, they go find other substrates, they do the reaction, they go find other substrates, and they can just keep on working. And so in order to understand enzyme function, we have to think a little bit about how chemical reactions work. Right? And so the nature of chemical reactions is that they only occur when the product is at a lower energy state than whatever we're working with. And so in order for the chemical reactions to happen, right, we have to bring our starting molecules, our reactants, up to an energy state where they're not comfortable. Right? They're not happy where they are, and so they're willing to react with other things. Right? And so we bring it up to a high energy, and then they'll naturally come down to a lower energy state. Right? So we go from our reactants to a transition state down to our products. So getting our reactants up to that activation, or rather that transition state, requires an activation energy. Typically, we put heat into a system, and that heat energy is enough to agitate the molecules. They move into uncomfortable energy states, and then they're willing to react. And so that's the general concept of how these reactions are occurring. There are other ways to utilize, or rather, input activation energy, right? Like light energy can sometimes be activation energy, but typically we use heat. Okay. And again, that's called the activation energy. That's how much energy you need to put in to get the reactants up to the transition state so that they'll come down to the product state. Okay. And so here I got an adorable graph, right? And so this shows us that we have to increase our energy, right? So we're starting with our reactants down here. This is our starting stuff. Right? We put the energy in, heat, right? It brings it up, right? Those molecules are shooting around and getting to an uncomfortable state. So they're way up here. And then when they're uncomfortable, they're willing to recombine in different ways that will bring them down to here. Okay? And so this is our product. These are our reactants. In this particular graph, I have it so that the products are a higher energy state than the original reactants. So this would be an endergonic reaction. This took more energy, right? So the energy went into this system. I could have it be the other way around. The reactants might be a high energy state than my products. So my products were down here. That would be an that would be an exergonic reaction. Right? That would release energy. Either way, you need activation energy for it to start. You need to bring those reactants up to the transition state either way, whether it be exergonic or endergonic. Doesn't matter. You do need to break bonds to make the reactions occur, so you need energy put in. What the enzymes do is instead of using that heat energy to get the reactants up to the transition state, is that by binding with the substrates and contorting them, right? We talked about the induced fit model in the structure video. Right? So when the enzyme grabs the substrate, it physically forces the substrate into that transition state. Right? It forces it into that uncomfortable state using bonding, like little attractions, like hydrogen bonds or ionic bonds around the active site. Right? Forces that molecule into the transition state. So instead of having to put energy in, we do it with the enzyme. And so the x-axis on this graph is time, right? If I don't have to use all this activation energy to get all the way up here and then wait till it comes down, right? So right here is where I got the products with my activation energy, old school, right? But if I can do that with the enzymes and I only have to get up here for my activation energy, I drop it down, right? My enzyme made this go a lot quicker, right? So I gained speed by reducing activation energy. And so that's the whole point, right? Much faster reaction, less energy required. Right? And so as I was saying, with the induced fit model, right, if this is the regular state of the reactant molecule, right? It's happy like this. It's like, I like being this shape, leave me alone, I'm not going to react with anybody, I'm cool. When it clicks into the enzyme grabs it, areas around the active site will engage with some parts of the molecule. Right? And so maybe down here is a little hydrogen bonding, it's attracting this, and this area is like a little ionic bonding, attracting this, and it forces it into this transition state. Right? So this is a low energy state, molecule's happy. This is a high energy state, this molecule's not happy. It's like, I'm willing to do some work with some other people right now if it gets me out of this uncomfortable state. Right? And on top of that, the induced fit model also forces the two substrates into alignment, right? There's a certain orientation that's required for the molecules to line up properly before they'll click. Right? They're physical things, right? If this is the clicky side and this is the clicky side, they have to be clicking together for them to work, right? So this is a reaction site, this is a reaction site, boom, magic. Right? If they bump in like this instead, no reactions. Bump in like this, no reactions. Bump in like this, no reactions, no reactions, no reactions. Only reactions. Right? And so without the enzyme, when the molecules are smashing into each other, they can smash in any orientation. Right? If they don't smash in the right one, they just bounce off each other. Right? Oops, missed opportunity. The enzyme makes sure that every time they smash in the right orientation. Right? And they're also smashing in the transition state. That way, it's assured that when they touch, reaction happens. Right? Much less energy is required, less time is required. It's just more better. It's mo better if you use an enzyme. That's it. Bye.